Do you love sushi? Me too. Tuna is one of the most commonly consumed ocean fish around the world. It's rich in protein and omega-3 fatty acids, but it can also contain high levels of methylmercury, which is a toxic compound that poses serious health risks to humans. Methylmercury forms when inorganic mercury released from both natural sources and human activities is converted by microbes in low oxygen marine environments. Once formed, it binds strongly to organic matter, entering plankton and biomagnifying up the food web. That's why large, long-lived species like tuna often carry the highest concentrations. People in countries with high seafood consumption are at greater risk of mercury exposure. Methylmercury is especially dangerous during pregnancy and early childhood. Studies have linked prenatal methylmercury exposure to developmental delays in children. In infants and fetuses, high doses can lead to cognitive difficulties, cerebral palsy, deafness, and blindness. In adults, mercury poisoning can affect fertility and blood pressure regulation. To track where this mercury is coming from, scientists use mercury stable isotope analysis. Just like any fingerprint, different mercury sources and processes leave behind unique isotopic signatures, which scientists can detect using instruments such as ICP-MS. By analyzing these signatures in ocean water, sediment, and fish, geochemists can trace mercury's origin. A key application of mercury isotope geochemistry is in understanding the sources of methylmercury in marine food webs that lead to tuna. For instance, a study in 2014 studied methylmercury sources in Northeast US estuaries. They measured mercury isotope ratios in sediments and various estuary organisms. The researchers found that the isotope values of most organisms could be explained by a mixture of methylmercury and inorganic mercury from sediments, suggesting that methylmercury associated with sediments is a dominant source for many estuary organisms. This was a crucial finding because there had been debate about whether sediment or the water column was the primary source of methylmercury in estuaries. The use of mercury isotopes provided a new way to distinguish between these potential sources. Another study in 2022 studied the sources of mercury in the North Pacific Ocean food web. They analyzed mercury isotopes in particles, zooplankton, and fish. Their analysis indicated that atmospheric sources are major contributors of mercury to surface zooplankton, and preferential uh, mercury occurs on small marine particles in the upper ocean. This helps understand how mercury enters the food web that eventually leads to contaminated tuna. Both studies exemplify how geochemical tools, particularly mercury stable isotope analysis, can be used to trace contaminant pathways and inform environmental management. Their findings highlighted different dominant pathways of mercury contamination in distinct marine ecosystems. The one in 2014 applied mercury stable signatures in combination with nitrogen and carbon isotopes to identify sediments as the dominant source of methylmercury to estuary food webs. And meanwhile, the study in 2022 investigated mercury cycling in the open ocean using both mercury isotopes and compound-specific isotope analysis of amino acids. Together, these methods not only enhance our understanding of mercury's environmental behavior, but also helps prioritize mitigation efforts based on source attribution and the biogeochemical controls.